Um, so Alan already summarized very well of the status of the both theory side as well as experimental side. So I can just kind of quickly add up a few more points and get into the some of my view. I don't have to tell you about this 2D materials, Van der Waals interfaces, but one interesting point is that there are a whole slew of the different type of the 2D materials, and then one can build up this the Van der Waals heterostructures. When we build up these heterostructures, we can choose the different materials, or very similar material, even the same materials with a different angle, but the phase space that we can explore in this type of system is really, really vast. Right, and especially if you start to include this different angles that which can engineer the Moira lattice. Basically, in some sense, without theory guide, what Alan did some years ago, 8 years ago, to just kind of where we have to look for. Often the experimentalist at this point is really clueless where do we have to really take the look at something. What are the interfaces we have to look at it, and now what is the angle that could be interesting thing we can just look at it. So I think in in that regard, this combination and theory, or more precisely, the theory guided experiment plays quite important role in this field of the Van der Waals interface and Moira superlattice application. Probably the first demonstration of this Moira superlattice do something comes in the very first demonstration, the graphene on boron nitride, which appears about kind of 7 or 8 years ago. I see that echoes, but hopefully that's, yeah. And then that simple system even lead into the quite interesting problems, such as Hofscherer's butterfly, seemingly just based on the competition between the periodic Moira lattice that engineered something like about 10 nanometer length scale with magnetic field whose magnetic length again that can be about 10 nanometer length scale, and that's where that the competition of the two different length scale plays kind of quite important role. Now, of course, the field really get excited 2 years ago that when Pablo's group at MIT showed that right at the magic angle that what Alan predicted that 8 years ago, that shows indeed some of this correlated insulating behavior that stemming from the very flat band formations, what theory precisely expected. Even more so that quite unexpectedly that when you dope this flat band system and move away slightly from this correlated insulating regime, the sample becomes superconductor, and that's quite unexpected, and therefore the very exciting the new efforts started happens, right? I would say that within 2.5 years of the time past now, I think right now the field is really kind of expanding rapidly. I just collect kind of some of these experimental papers that I can quickly search through. Of course, in twisted bilayer alone, the magic angle twist bilayer alone, not only correlate insulator, but superconductor. Alan mentioned that there's magnetisms, quantum anomalous Hall effect has been seen in those kinds of systems. And then the people quickly search the beyond this twisted bilayer, for example, the tri-layer system, where the flat band appears, either aligned with the boron nitride, not aligned boron nitride. This tri-layer system also shows the correlated insulating behavior, superconducting behavior, as well as some of the quantum anomalous Hall type of the behavior. And there's also not only the magic angle twisted bilayer, but you can just put the two Bonner stack the graphene layer to form so-called this twisted double bilayer. And there has been also a demonstration the correlated insulating behavior, plus that some sort of spin polarizations of the decorrelated gap and potential the superconductivities, and those kind of things has been reported by many research, many experimentalist group. And also as Alan mentioned, now that not only graphene like the system, that system get expanded into the TMDC and TMDC, the transition metal dicharcogenized system, either homojunction or the heterostructures with a very similar lattice parameter. There has been quite an exciting the report, such as correlated insulators, that Wigner crystal formations and all this type of things actually starting appears in this Van der Waals twisted layer system. Another interesting aspect of the experimental side of this twisted bilayer system is that not only transport measurement, but other experimental tools, especially the scanning probe, can be readily accessible. So there has been already a couple of the STM work that's showing the interesting electronic structures in coordinations with the atomic registries in the magic angle twisted bilayer or close to there. Couple of STM work as well as a scanning probe work to show this local compressibilities measurement as well as a local field dependence measurement by the scanning squid shows this the electronics and the magnetic property in the local. I think this type of the trend will go on, especially this local property plays quite important role. And also Alan briefly mentioned that some of the TMDC system that because it's a gapped semiconductor with the gap close to kind of visible light, one can apply a lot of the optical techniques that can see that various optical effect, especially that extern's confined or extend field is Moire pattern, Moire potential, plays a quite important role in past few months. And there are quite a lot of publication and research activity goes on. So I think that's probably the general aspect of where that experimental status and what is going on in the experimental land to just kind of take a look. But also we are facing quite of the challenges on the experimentalist side, and that's kind of something I want kind of briefly share. Using my own experiments as a tool that kind of deliver that what is the challenge we as experimentalists are facing. I think I heard that David Gordon is there. He can also share some of these view in a moment, but let me start with my experiments to share the idea. So I will start with this phase diagram, which actually has been played an important role a couple of times already, right? So this is the very first phase diagram of the density versus temperature axis of this twisted magic angle twisted bilayer graphene done by the MIT group, right? So here is a twisting angle 1.16 is 1.05. They're qualitatively they're quantitative difference, but qualitatively similar. Basically, that it seems like the multi-insulator is dividing of this superconducting dome. There seems like there's some sort of competitions between the insulating phase, correlated insulating phase, as well as the superconductivity in the system. Now, the few months later, about a year later, I think that this is the status art of the sample that prepared by Dmitry Afetov's group that Alan showed. The phase diagram is now a little bit different. Not only that the one insulating regime that originally they studied, the superconductivity appears in many of this side of this other type of the correlated insulating regimes. Not only a half field, the quarter field, three-quarter field. There's also insulating regime appears, and nearby that insulating regime, if you go down enough, that there is a superconducting like the states appears in the in this type of the sample. Even more so, the most recent the report done by this one is Andre Young's group, and I believe the Caltech group showed the similar things. Also start to demonstrate that different angle, slightly away from the magic angle, and they also see the superconductivities in the low temperature. But in this particular case, there is not necessarily that right next or nearby the correlated insulating regime. So there is some speculation experimentally, at least in this angle of the sample, the superconductivity might be the separated issues with the correlated insulator that people have seen. Now, the trouble here is, seems like every sample looks a little bit kind of different type of the phase diagram. And there is of course, as the sample quality progresses, we see the more of the details that could be, but also kind of different angle, slightly different angle shows a kind of rather different type of the physics where the angle may not necessarily in the exact control of all the experimentalists, right? I think we often that target some angle and we end up with kind of slightly different angle. We tend to study about that. So one of the joke among the experimentalists is every sample make one separate phenomena and separate the papers out of it. So the issue here is how we can control precisely the sample we are studying. I think that could be one of the issues. It actually ties with even in the one sample. There's kind of raises some of the issues. How well we can control the angle within the sample. Of course, if the physics is really sharply tuned by the angle of this twisting, in other words, that the more superlaris the size, it must be quite important that to have this uniform the distribution of this angle, at least within the one sample that we study. Well, it turns out that's probably not the case as you expected, and there is always a disorder, including the certain angle distribution. So this is a paper that done by the Alice Zeldov's group using scanning squid. They image that what is angle distributions of this closed matching angle twisted bilayer sample that provided by the MIT group. And they see that, yes, it is in average close to the magic angle, but there's substantial the distribution of the angle, depends on the sample. And this will just tend to create this, especially when you get into the superconducting regime, some of this population pathway of the superconductors throughout the samples. And when the population is made, then between the voltage probe, you can read out this superconductivity. But if not, then you just don't read it. So certainly we can imagine that sample inhomogeneity plays quite important role when you use the transport as a tool. And very similar experiment also shows up in this case that scanning SAT made of the nanotube done by, again, the Weizmann group to demonstrate this imaging capability shows that the fine distribution of the angle in the system. So one way that we can get around this type of the idea is there a way that we can bring this magic, the flat band, not just controlling the angle, but controlling some other parameter in the system. So there comes the one of the idea using this twisted double bilayer. So around kind of similar times, there are a few groups actually now trying out this the idea of the twisted double bilayer. And the idea is kind of following. So if you just think about the Bonner stack bilayer, just the two graphene layer stack into the registry, basically there's inversion symmetry between the lattice point. So if you just break this inversion symmetry of the Bonner stacked bilayer, in fact, that you can open up the gap into this charge neutrality point of the spectrum of Bonner stacked bilayer. And this has been demonstrated by many experimental groups and by optical measurement, transport measurement, by applying the descent displacement field in the vertical direction of this plane. One can open up the gap about the size of something like the even 100 millielectron. So idea is that once you just stack this twisted the two Bonner stack bilayer and make the twisting, there's a possibility that that you can just create this hybrid gap, and then by just applying the electric field, that you can probably open up the gap and then control this the size of the flat band by just controlling the displacement field. So in some sense, in this particular case, you don't necessarily sharply tune the magic angle, but whatever angle that close to the some small angle, you can use the displacement field to control this band structure such that you can just control the flatness of this band. Now, this simple idea, in fact, was taken a little bit more the serious the calculations, including both of the displacement field and all this layered coupling, that this was done by the Aspen's group. Then the conclusion is following. Well, if you have something like around the 1.2 degree to the 1.3 or 4 degrees of the twisting angle, by applying the displacement field, creating this the imbalance of these energies between these two Bonner stack bilayer, which in this case control the parameterized U, you can isolate this separate band, whose bandwidth in fact controlled by this U. So somewhere around these regions of the displacement field and the angle, you should be able to get the reasonably well isolated the band with bandwidth is as small as something like the tens of millielectrons. So that's basically the idea behind of this twisted double bilayer. In fact, this idea works. So this is a twisted bilayer sample. And then here that we need the two gate and top and bottom to control both the filling and the displacement field. And you start to see that in this the charge neutrality point, you open up the gap, which is basically a single particle gap that again, by applying the displacement field, that the gap opens up. And full field, the full filling, there is also gap opens up. And again, this is a single particle effect that I just mentioned, that the moire superlattice will create this the band folding, and they create the single particle gap. But interesting enough, that between this the neutrality with the full filling, and once that you get the half filling, that this dark color means that large resistivity appears, and that only appears at the finite displacement field, which actually flow in that directions, right? So this basically the appearance of the high resistance state, indicating indeed that there is the insulating state that we can stabilize by this displacement field in half field ranges. One can do a little bit more careful work. For example, that you can just measure the size of the gap, and gap in this particular case about 1.33 degrees is something like a few millielectron volts. So sizable the gap appears, and you can apply the magnetic field and just kind of get the band mass around there. And band mass is much more enhanced by the single particle, the band mass that estimated the band structures near this the half field gap, indicating this half field gap is indeed that likely the correlate gap that one can get similar in the magic angle twisted bilayer, except that here, that in a sense, magic angle is realized by using this the displacement field as control parameters. And one can actually study about this nature of the insulating gap, applying the in-plane magnetic field. It turns out when you apply the in-plane magnetic field, this half field gap that I just mentioned becomes much stronger. The size of the gap actually increases. Not only that, previously that we didn't have anything signatures in the quarter field side. Applying the in-plane magnetic field, we actually start to stabilize this gap in the quarter field states. So in a sense that there is a half field gap and quarter field gap states gap appears very similar to the magic angle, the twisted bilayer graphene. But in this particular case, first the gap is stabilized only with this displacement field. And the gap is actually strengthened by the in-plane magnetic field, which actually increases the Zeeman effect, Zeeman gaps. So from this, at least we start kind of contemplated that this correlated insulating gap that we have is likely the spin polarized gap. In other words, it is basically spin polarized band or ferromagnetic, the ordering that happens due to the correlations that we have. So that's the one thing that we start to see in this type of the sample. Now, natural thing we can ask is now, okay, so we start to see that these gaps that potentially the correlated effects. Then what if that we just kind of slightly away from this gap and dope these samples like the twisted bilayer graphene? Do we see something unusual? Indeed, when we just kind of tune our angle even smaller, such that bandwidth becomes even smaller. And indeed, we start to see the very similar things. Again, that there's a halo that regions appears, that where that this half-field correlated insulator appears. And they turns out this half-field correlated insulator is also spin polarized. And with this even narrow bandwidth system, when you dope it, we start to see that system shows that the superconducting like the transitions, that finite resistance drops quite rapidly and get into zero resistance. And then once you get into this zero resistance state, we just measure the IV, and the IV shows a strong nonlinear behavior. And this nonlinear behavior, with the temperature and magnetic field dependence, actually clearly following through this BTK type of the transition behavior, and strongly suggestive that this might be related with the 2D superconductivity we measured into this type of the system. So that is another exciting thing. So similar kind of following through the very similar footsteps that what has been shown in the magic angle twisted bilayer, maybe many of this twisted bilayer system also shows this the correlated insulating behavior, and upon the doping this correlated insulator, maybe you may see that superconducting like the behavior. Now, that's the exciting part, but here comes that experimentalist nightmare, right? So we start to explore that this system with a kind of slightly different angles, right? And one of the motivation I mentioned is when we have this different angle, that in principle we can tune this the displacement field to bring the flat band into the reasonable distribution of the angle. It is true that the between that 1.2 to say 1.5 degree ratio of the twisting angle, we should be able to realize this the correlated insulator, spin polarized correlated insulator by tuning the displacement field, and that kind of here shows all the kind of demonstrations. And that then when we measure this doped the correlated insulator region, we do see that generality that indeed in these regions that where the near this correlated insulator region, so we see that the resistance drops rapidly to a very small value, close to zero, but not all the samples. So it shows that zero resistance. I have 3 minutes. Is that what you're saying? Okay, 5 minutes left. Okay, good. Thanks. Yeah. So and then basically. Just one sample out of say 5 or 6 samples that we tried out shows that kind of so-called zero resistive behavior. Now that we have the really kind of push into the limits, whether can we really claim the superconductivity based on one sample and only the zero resistance. I think this could be that equally applicable for the many other 2D systems. Probably magic angle twist bilayer, there are a lot of the growing evidence that indeed the superconductivity observed in many different samples, and including the phase coherence behavior. But some of the other samples like this, the twisted tungsten diselenide, where that also you see the very low resistance state shows up. But it's a very, the particular conditions and a few of this, the gate choices, it's not clear that whether just a zero resistance state alone that one can claim the superconductivity, and one should be able to see other possibility in this type of the sample. So the problem that experimentalists that face is there a way that we can get create the homogeneous sample in the reliable way, or is there other type of the measurement other than transport, preferentially some of the thermodynamic type of the measurement to follow about this superconductivity as well as correlated insulator. So that's kind of the one of the issues. The part of the problems that we are facing of the such a complicated behavior is indeed the part that when we stack these samples together, it's very difficult to avoid to just the distribution of the built-in strains, and built-in strain is naturally ends up with this angle modulation. This is one of the extreme case that I'm showing you that what happens that in the twisted bilayer sample that we target is something like the 0.5 degrees or 0.4 degrees. There can be quite of the distribution of this different type of this Moire patterns, which often that average it out when you just measure it. So unless we really carefully tied with our the local the probe that seeing that what we are measuring is what we are really targeting, sometimes it can be often just the confused with the experimental data. I think that's kind of one of the situations. But the other thing that we can mention here is often that this type of this Moire patterns formations or this structure disorder kind of formation is also the opportunity for the experimentalists, because this in fact can be analyzed in terms of the new type of the structures, especially this Moire pattern. Not only the electrically it's the fold of the band, but structure-wise that this Moire patterns can be interpreted as the combination or the junctions of the dislocation, structural dislocation line, or the two dislocation line, where especially in twisted bilayer, there is a topologically the protected 1D mode is running through along this Moire lines. And it turns out that when you just kind of investigate the dislocation line network, or this 2D dislocation network, another way of the interpreting this Moire lattice, that is strongly the topologically protected the object. Let me just skip through because of time. There is a really well developed mathematical tools. You can just analyze this type of the 2D Moire network in terms of this dislocation network in topologies. And in that pictures, basically all this, the AA site is interpreted as the kind of one of this vortex site, right? And moreover, not only the twisting, there's a way that you can create this type of this general de Moivre lattice even further, right? You can create this the vortex and anti-vortex array by just twisting or shearings, and then the isotropic expansions or uniaxial expansions, and all of this thing created different type of this, I would say, Moivre patterns, or in other words, in equivalent languages, basically network of these dislocations with different kind, and they tend to actually shows very different structural properties and potentially the electronic properties that associate with that. I think once we expand this, our challenge is that it's a very difficult to control these uniform layers. Maybe one can also expand that our the now challenge into the opportunity. Can we study about this type of this network that that one can engineer into this model? I think that's kind of one of the ongoing efforts, which could be quite exciting directions. I know my time is up, so let me just kind of close it down. By the way, all these things can be also controlled the electrically as well. So I think I will just kind of close it down showing this movie. And this is a movie that's showing that one can create these model patterns and put this top and bottom gates that one can control the displacement field. Now, this is TMDC layers, and in TMDC layers, by the way, that this all the Moivre domain contains their built-in the dipole moments, such that when you apply the displacement field, this dipole moment can be coupled with the electric field, such that the domain size becomes smaller and larger, right? So especially when we're dealing with this twisted bilayer cases, that by applying this displacement field, not only we change electronic properties, but in a sense we also change the lattice properties, lattice size, by just kind of this electric field. So I think that's the one thing that I want to mention as a kind of another interesting opportunities. So the summing up, basically experimentalist that is facing the exciting moments, exploring a lot of different interfaces with a lot of different electronic properties, but also facing with the challenges, how we can control the sample, and how do we know that what we are measuring, and how we can make this kind of the control even better. All right, so yeah, okay. So let me just kind of skip this one. And let me thank my collaborators. I think that a major experiments part that twisted double bilayer that I mentioned is done by the Xiaomeng Liu now at Princeton, and the J.U. Hao working in the project with the theory support from the Aspen's group and Tim Cox's group. And there are a few other systems I briefly mentioned. Thank you very much.